Hi everyone, my name is Shashank and I'm a data analyst on my journey to become a data scientist. And in that journey, I'm going over the book Hands-on Learning with Scikit-Learn Keras Tensorflow, second edition. And we are going over chapter 7 today, which is over ensemble methods and random forests. They say ensemble and random forest, but the author really seems to be singing the praises of gradient boosting for a good section of the chapter. So they should probably rename it, but let's just get to it. So for anyone wondering, this is the part 6 because I didn't do a chapter on chapter 1 on this series where basically I read the chapter, I compile my notes on it, make some custom code, and then I give that all to you guys. The code and the notes are separately available on my Patreon. It's a great way to support what I do, but you can see all of the notes in this video. Like I'll be talking off of these notes and I'll be scrolling through the notes and showing you everything on them. So the knowledge is readily available, but the convenience is the ability to access the notes in through my Patreon. So let's go ahead and get started. So what are ensemble methods of machine learning? It's basically when you take a number of machine learning classifiers and you put them together in some configuration in order to create a more accurate classifier. There are many different methods to doing this, and we're going to go over a couple of them in this chapter. So the first one we're going to go over is something called voting classifiers, where basically what you do is you take 4 different classifiers, 5 different classifiers, some number of classifiers. So for example, maybe like a decision tree, a linear regression, support vector machine, and you have them all, you train them all in the same data, have them predict on that data, and then they each basically vote on every instance as to what is the most accurate prediction. And so, for example, let's say we're doing a classifier, right, where you need to classify between classes 1, 2, and 3, and you have 3 different classifiers. And the support vector machine and the linear regression both say, oh, this belongs, or well, the logistic regression, I guess, this belongs in class 1, and the other regressor, the decision tree, says, oh no, this belongs in class 3. Well, in that case, you would a voting classifier would take the outputs of all of these different classifiers together and pick the one which has the most votes inside it. Now, there are 2 ways you can handle voting. There's something called hard voting, and these can work really well even when independent classifiers are not all that great. And the book is a really great example as to like why this is the case. So, for example, like pretend you have a coin, right, that has a 51% chance of actually being flipped heads instead of the regular 50-50. And we'll call this a weak classifier. So for example, let's say the classifier is picking between 2 classes and it only gets it right 51% of the time. Well, the thing is, if you flip that coin over and over and over again enough times, the chances that a majority of the flips will be heads actually increases with time. He doesn't really go over the math in the book, but like if you think about it, it makes sense because it's going to want to approach 51% every time you flip the coin. It's a law of large numbers. And because of that, these classifiers altogether will collectively eventually get to the right answer most likely. And that's kind of the example that Garone produces in order to illustrate why a voting classifier, even if the individual machine learning algorithms are quite weak, why a hard voting classifier can actually be quite accurate. On the opposite end, we have something called, oh, and I should probably go over what a hard voting classifier is. So a hard voting classifier will basically take the predictions from each instance, and the one with the majority of the class that's been predicted the majority of the time is the one it'll use. Versus a soft voting classifier, it will basically pick the class with the highest class probability averaged across all classifiers. Now, this assumes that the classifiers can actually estimate class probabilities, like the probability that something will be in class 1 versus class 2, instead of just saying, oh, it's going to be in class 1, it's going to be in class 2. And you can determine if classifiers can be soft voting classifiers using the predict proba method. So if we want to actually create a classifier, it's actually quite simple. From sklearn, the ensemble class, we bring in a random forest classifier and a voting classifier. And we bring in, sorry, yeah, you just bring in the voting classifier. I don't actually believe, oh yeah, we can use a random forest over, yeah. So sorry, yeah, you bring in the voting classifier. This is the key over here. And then what you do is you have your 3 different machine learning algorithms, right? In this case, where we want to do a logistic regression, a random forest classifier, and a support vector machine. And all you do is you create a voting classifier class, you instantiate the voting classifier class, and then under the estimators parameter, you go ahead and just create a list, or I guess you could create a tuple too, but a list of the name of the classifier and the instantiated class of that classifier. and then you just run it as so. And what this actually does, this for loop over here will actually run the classifiers independently, and it'll show you how oftentimes the voting classifier will perform better than any of the independent classifiers, although that's not always the case. Going to the code, I actually went ahead and downloaded a dataset from Ben Rochon, and it is factors affecting campus placement. Basically, what happened was there is a dataset where they are looking at, or I can probably show you guys. Can I just click on that? Yeah. They got a bunch of data from a college, and they are trying to determine, okay, what can we predict the employability of a candidate? So you have things like work experience, what degree they have, what percentage of the degree they finished, stuff like that. And then, so I took that data set and then I cleaned the data set. And the reason I went through the whole cleaning process, even though that's more of a chapter 2, chapter 3 thing, is because the actual, like, when you're actually like doing machine learning, right, the actual like execution of a machine learning algorithm is not that difficult. It's getting the data in a format that will work well with the algorithm that I believe is the harder part, and where you need to have a really good head on your shoulders as far as how this stuff works. I work with a couple of data scientists at my company, and the amount of time they spend cleaning data and like getting data into a format where they can easily tune the parameter, or where they can easily use it with machine learning algorithms, it seems like that itself is a very important skill. So that is what I'm doing for a good chunk of this part over here, checking data types, doing some data cleaning. So we are dropping the first column because that is just a serial number column, and we can't really. I don't believe we can actually predict anything on that. That's just a primary key for the table, and we're also dropping the salary because the salary is something that could only be predicted after someone has already gotten a job. Which is why you can't use it in your classifier, because it's information that you would only have access to after you've already created the classifier. So we can't do that. And then we are encoding gender, work experience, SSC, HSCB, and specialization. And we're just using label encoding on this. And I had a live stream last night where someone asked me a great question: why use or why use one-hot encoding instead of label encoding? Well, label encoding, what it does is it'll give a different number for every single instance, or every single class inside a column. So, for example, well, let's take genders, for example, right? Like, these days a lot of forms will allow you to fill in male, female, and other, or male, female, and then their whatever other options are available. And in that instance, what happened was, you might say like male is 1, female is 2, other is 3, giving each of those a different number. And what that does, that automatically creates a relationship in that data that doesn't already exist. Like, why? Like, is by other being 3, is it 3 times male, which is 1? There is no numerical relationship over there. And that's why we can't use a label classifier for classes, or for columns that have more than 2 classes. Versus, for example, say you took a more traditional male-female or like gender selection box, right, where it just says male-female. In that case, you could use a label encoder, because you could just make female 1 and male 0. It's just binary at that point, and there's no numerical relationship between these two, or the numerical relationship is very limited. So that's why we want to use one-hot encoding when you have more than 2 classes. I think you could have like 3 classes and label encoding still fine, and it depends on the algorithm. Honestly, like, algorithms these days are getting so smart that they do so much of the work for you. Like Catboost, for example, will do all the encoding for you and handle categorical variables and stuff for you. But as far as like how we want to traditionally handle this stuff, you want to use label encoding when you have 2 classes, and then a one-hot encoding when you have more than that. So gender, work, X. So these are all columns where I know that there are only 2 classes of data, and that's why I'm just using label encoding over here, versus I will use one-hot encoding for status, because, or for, was it status? No, not status, for the other variables, because I know that those oh yeah, like degree and stuff, because I know that those have more than 1 or more than 2 options inside them. And I just learned about the pd.getDummies method, which is amazing. Instead of like bringing in Scikit-Learn and using their whole method for trying to like use one-hot encoding, pandas will automatically do it for you using the .getDummies method. So I'd recommend just using that instead of Scikit-Learn. I'm not a big fan of like the way Scikit-Learn does a lot of its data cleaning, and it really like Scikit-Learn's like really like into like using NumPy for everything. I'm guessing it has something to do with speed, but I honestly just am more comfortable with pandas, so I'm going to be using that. And then we go ahead and scale our data. I actually forgot to do this initially, and the algorithm started yelling at me. And so we went ahead and scaled our data, and you can see once we scale the data using Scikit-Learn, we get a bunch of NumPy arrays, which are very difficult to read, and I'm not a fan of NumPy arrays, or when I could be using pandas. But my understanding is that NumPy arrays are faster when you don't faster in certain contexts. So, and then what we do over here is we're basically just running the this is that same code I showed you guys earlier, and we just ran it to see what the accuracy of the actual. Let me go ahead and just run it all. I think I can just do that. Might take a second to run. Yeah, it's glitching out a little bit, so you know it's running. Yep, there we go. We got the check marks over there. And we'll see, in this instance, it looks like the voting classifier just did as well as the logistic regression, which was the best predictor. But at least we know it didn't do worse. So that's how a voting classifier works. So we've run our first ensemble method. Congratulations. And that is how voting classifiers work. And if you want to use soft voting versus hard voting, there is this voting parameter in here, this hyperparameter voting that says hard. Just change that to soft, and you can automatically use soft voting. So congratulations, we've done voting classifiers. Let's go on to the next part, bagging and pasting. So previously, we've trained a diverse set of algorithms on our training set so that we could train, sorry, let me back it up for a second. Previously, what we did is we took 3 different algorithms and then made them all vote to decide, okay, which one is the most, which class is the most accurate class for what we're trying to do over here. And we ended up having, and we ended up picking the logistic regression as the algorithm that worked the best. But what if we wanted to use one algorithm and just train it over and over and over again? Well, that's where bagging and pasting comes in. So what happens is, if you can use this to train one algorithm on multiple subsets of the data, and if you replace the training subset before picking your next subset, that's called bagging. And pasting is basic, and bagging stands for bootstrap aggregating. And if you're not replacing subsets, basically you're just picking a subset and then training the algorithm on that, and then picking another subset, training the algorithm on that. But these 2 subsets are completely different from each other. That is called pasting versus bagging, which is like you pick one subset, train an algorithm on it, put it back in, pick another random subset. You might have a couple of the same instances from that subset, train the algorithm on it, put it back in. That's called bagging. And bagging apparently creates more diverse subsets with slightly less bias than pasting, and predictors end up being less correlated because the data sets are more diverse than with pasting. So bagging is generally preferred because it will usually create better models. Then we have something called out-of-bag evaluation. So when you're bagging, there are instances that'll be sampled multiple times, obviously, and some instances may not be sampled at all. And the non-sampled instances are called out-of-bag instances, and you can actually use these as part of a validation test set. And what this does is the validation test set, sometimes people ask the validation set, sometimes people ask what is the validation set? So you have your training set, your test set, and then sometimes you have a validation set. Sometimes your validation set is used to predict how well will this work on the test set. It's kind of like a secondary test set, except you're allowed to look at it more than once. So a good ML practitioner will not look at their test set until the end of the actual problem. That way they can prevent biases and trying to fit to the test set of data. So a validation set lets you kind of look at a test set without actually doing that. And here is a simple example of how to create a bagging classifier. And if you change bootstrap to equal false, you change it to a pasting classifier. Got to drink my coffee. All right, next. Let's go ahead and talk about random patches and random subspaces. So random patches refers to using random features in training instances to speed up training, while random sampling, just features, is called the random subspaces method. So for example, remember, samples are our rows of data, and features are our columns of data. And random patches is basically using random features and training instances, so columns and rows, in order to speed up training. Basically, you're using a subsection of the data. Versus random subspaces, you're only using random features, I believe. And you can activate random patches using the max features parameter and the bootstrap parameter. Very short section inside the book. Next, we're going to go over random forests. And random forests are simply an ensemble of decision trees. Take a bunch of decision trees, put them together, and you have a random forest. Excuse me. And it's usually an ensemble put together through bagging. So you can actually create one manually, and he does this in the book, where he creates a random forest by manually creating a bagging algorithm with multiple decision trees And that's just a recreation of the random forest. But random forest is a method that's inside sklearn that like does this with some of the best practices out there. I think the classifier, what they do is they introduce extra randomness in order to generate a better model that is more biased and has less variance. Remember, bias and variance are two sides of the same coin. You can't have, you can only have one at the reduction of the other one, you know? So we have our bias and our variance over there. At one point in time, you know, you can obviously like reduce bias and variance together to a point, and then you can also increase them together to a point. But then after a point, it becomes a trade-off of picking bias or variance. I believe that was chapter 3 or 4, but we did go over that. Now, a really, really cool benefit of random forest is that you can get something called feature importance. And what feature importance tells you is it tells you, okay, I'm a classifier. I've picked out class 1, 2, or I picked class 1 as the most likely class. What features, remember feature just means column, what features were most important in my decision making? And this is a very, very important lesson. And let me tell you guys a story. So I work at Nordstrom, a major North American fashion retailer, and we are currently working through some forecasting exercises. Now, it's very important, especially when you're doing forecasting, right? You can use some algorithms out there that will give you a very accurate forecast, a statistically accurate forecast, but they're not very good at telling you why the forecast was the way it was. So when you go to a business partner and you tell them, hey, this forecast is super accurate, but I can't tell you what's influencing it, that doesn't really help them because they have a hard time explaining it to their higher ups, and they have a hard time influencing that forecast, you know, increasing inventory, increasing, decreasing staff, stuff like that. Like, they have a very difficult time actually trying to execute on the data you've given them because you don't tell them why the prediction is the way it is. And this is where you have an instance where it might be more important to have a slightly less accurate classifier or slightly less accurate regressor in exchange for something that can actually that is more explainable. Explainable AI is very important these days. And you know, my personal theory as to why this is the case is because around 2014, 2015, you had all these algorithms coming out, a lot of deep learning stuff, a lot of boosting stuff. And all these algorithms were coming out, and people were like obsessed with actually creating the most accurate algorithm out there and the best algorithms out there. But what happened was people were executing these algorithms in the business world, but no one knew why things were happening the way they were. Everything was a black box, and that's where explainable AI is kind of all the rage right now. Very important. I'm not actually a data science practitioner, so do take what I'm saying with a grain of salt. This is kind of what I've observed in my experience, and that's why feature importance is so important. And random forests are excellent for this. And people, you know, we use random forests right now when there are better algorithms to be using because random forests are so easy to explain. And if you remember our chapter on decision trees, you'll understand why it's so easy to explain a decision tree. I actually think that might have been the last chapter. So over here, using this code over here, you can easily create a feature importance like list. So let me go down here. So it's a little bit hot outside, so my computer's a little bit slow. But you can see we can get the feature importance of each column, and it seems that SSCP is very important, and HSCP is very important. Oh, nice. So I'm outside right now, and there's like just a Porsche 911, like just cruising down. It sounds so nice. And we can see that, for example, MBA seems to be a very important feature as well. And HSC or SSCP is probably the most important feature. Now, what is SSCP? Let's see. I had a list of all of the features at the top. Secondary education percentage. Okay, that makes sense. So the amount of secondary education is probably very indicative of whether you're going to be employable or not. So that's how you can look at feature importance. That's one of the reasons we like random forests so much. Now we get to the meat. We get to boosting. So boosting methods are what they do is that they take, so actually let me back up for a second. Boosting is all the rage, and there was a point in time, I don't know if this is still true, but basically like XGBoost and all these boosting algorithms were the ones that would basically win all of the Kaggle competitions. So boosting is definitely something to take a great look at. Some motorcycle downstairs. So boosting is kind of all the rage, and the thing is like boosting is I think boosting came on the heels of deep learning, and while deep learning very much like has its place and like stuff it's really good at, so for example it's really good at like image recognition, speech recognition, it's also a algorithm that they're also a set of algorithms. Deep learning algorithms are a set of algorithms that require a ton of data, and are very, very, very difficult to explain. Like they are like the epitome of black box models. So that's where boosting comes in. And boosting actually, a lot of boosting algorithms can be a lot more explainable. They actually do have the ability to show you some feature importances. And boosting basically is another ensemble method. What it does is it tries to take a bunch of weak learners and then combine them into a strong learner, as we do with all of our ensemble methods. And the way it does that is it trains several predictors, and then what happens? It'll train a predictor, right? And then it'll take the inaccuracies of the last predictor and try and correct for that in the next predictor. So each subsequent predictor is correcting for the inaccuracies of the previous predictor, which leads to very good outcomes. So let's go over Adaboost now. So Adaboost stands for adaptive boosting. And basically what it does is it will work with each predictor and pay more attention to the training instances, which are being underfit, and then progressively train them more and more. So this is the visual that they give us. For example, here's your original training data, tries to train something. Okay, so it looks like it didn't fit this one very well. That was underfit. So then it'll try and make the predictor fit to that. Okay, so now a bunch of other stuff is underfit. So now we make this predictor over here, and it keeps doing that and trains the instance weights each time. And that's what Adaboost is like good at versus gradient boosting, which we'll get to in a second. So that's how you would run an Adaboost classifier, fairly simple. And then next we go over gradient boosting. And then like Adaboost, same basic idea, but what it does is it tweaks the but where Adaboost tweaks the instance weights at each iteration, gradient boosting actually fits a new predictor to the residual error. So basically, how far away were you, and all the residual errors of the previous predictor. And a couple of the hyperparameters that are important are the learning rate, warm start, subsample, and loss. I'll start off with loss because that's the easiest one. That just allows you to change the cost function used by the boosting algorithm. Then you have subsample, which specifies the fraction of training instances you want to be using for each for training each tree. And this method, and when you use a less than all of the samples, then you're doing stochastic gradient boosting. And the reason you might want to do that is if you want your training to go along a little bit faster. Then you have something called warm start, which basically what happens is it lets you keep the existing trees every time you run the fit method. So you could run the fit method over and over again and see, okay, like, has the algorithm fit to an acceptable standard for me or not? It lets you like manually basically run the algorithm over and over again. It's like, warm starting versus cold starting a car. And then learning rate, lower learning rates basically will need more trees to fit the training data, so they'll be slower. But they create more generalizable models. And then when you reduce the learning rate, that's called shrinkage. So to implement a gradient boosting classifier, you'll just do it like so. Fairly simple again. And I just added a small section over here for 3 other boosting algorithms that weren't mentioned too much in the book. He did actually mention XG boosting. XG boosting just stands for extreme gradient boosting, and it's a algorithm created by this guy named Tianqi Chen, I think, and he created it as part of like a thesis or something. Like the kinds of stuff some people like are able to make while in school is freaking insane. Like, I mean, I think he's probably doing some like PhD paper or something, but still, like how smart some of these people are is freaking crazy. And I'm here, I'm like, XG boost execute. Just wanted to put that out there. Like, if you think what we're doing here is crazy, you should just see like what people that are like spending their entire lives studying the stuff that they're doing. CatBoost stands for categorical boosting algorithm, and basically it is an algorithm created by Yandex in Russia. So they don't like being called this, but they're the Google of Russia, basically. But they do a lot of other stuff too, kind of like Google, outside of just like the search engine. And it's a high performance algorithm that works really well with categorical variables. And an algorithm that I've used before and I really, really like, and you don't have to pre-process the categorical variables nearly as much. And actually, you're not supposed to one-hot encode when using cat boosting. And then LightGBM is a gradient boosting algorithm created by Microsoft that's actually very lightweight. And I've used it before when I just didn't have computing power to use other boosting algorithms. So that is another thing to look up. And what I'm trying to do here is I'm trying to like show you guys like, like go look this up, go look that up. Now that we've like gone over this chapter, you can go explore and see what you actually want to execute on. And let's just take a step back and kind of see like how do we actually want to like, what's the point of all this stuff we're doing right now, like with this book and everything, right? So I'm going through the book, and the idea I want to get through the book is to understand the broader space of machine learning, have some understanding of the basic fundamentals of it, and then that way whenever I'm encountered with a problem in relation to machine learning, I now have some basic building blocks I can use to construct a solution. And that's what we're trying to do over here. So when I just throw in these things and don't give much information, it's kind of because like I will probably create a video in the future where I actually do an entire like video on the cat boost algorithm. But I just want you guys to be aware of what building blocks are available out there. That way you can look them up as you need to solve whatever problem you need to. And then finally, they go over stacking or stacked generalization. And it's another ensemble method which simply refers to using another model to perform the final aggregation step of the predictions, um, using either soft or hard voting. So what happens is you have multiple different classifiers. They all put out their predictions. You take all those predictions into a model and then try and make a prediction out of that model at the end. And Scikit-Learn doesn't have an API to actually handle this by itself, but it's relatively easy to code based on what he says. Um, and maybe I'll put out a video later where I actually create, but I didn't really bother creating one on this. I'm trying to get through this book as quickly as possible because like I've kind of learned like at least in the like corporate world, there's for the type of work I'm doing, there's not much of an incentive in like learning something like all the way to the deepest core, like there is kind of in school. It's kind of like just learn enough to like basically understand it, and then just keep executing. That way, you can actually solve whatever problems you might have. So you'll notice that like when I go over these chapters, I highly recommend you read the chapter yourself and like use this as like a review, and then two, you might notice that like oh, he's kind of like giving a bit of a surface level view of the chapter. And that's mostly because I want to kind of just like summarize what's going on in the chapter. Remember to like, comment, and subscribe on my videos. If you can't support me through Patreon, totally fine. That is an excellent way to tell YouTube that my videos are worth watching and people should actually watch these videos. And I think they are something special. You know, I mean, a lot of the content I put out, I feel like is very substantive and like it's like me showing people how to actually do things. And I really want YouTube to have a little bit more of that content on a regular basis. And so liking, commenting, and subscribing is a great way to show YouTube, hey, this is content worth watching. And if you're able to, Patreon is another great way to support me and make sure that I'm able to continue doing this. As I get more more revenue through Patreon, I'm able to offload my other side projects and spend more time on YouTube. So, for example, like offload some of my consulting and spend more time on YouTube because it's more financially viable for me to do so. So, thank you guys so much for watching, and I hope you have a great day.